Hi, my name is Jeremiah Lee, and today I'm going to be sharing some ideas that I've been thinking about for a decade from my work on Fitbit smartwatches, Spotify Connect devices, and e bikes. I call it leaf computing. It's what I think comes next after cloud computing. It's both a complement and a replacement. And it's what I think is necessary, both technically and politically, to rebalance the power of technology back to empowering users first. So, to explain this, I'm going to share a few stories. In 2015, I spent a week hiking in Banff, Canada. It's one of the most stunning national parks that I've ever been to. Banff is filled with tall mountains, deep valleys, and wide glaciers. Along with my usual hiking gear, I had my Fitbit fitness watch and my smartphone. My Fitbit smartwatch recorded my GPS location, steps, heart rate, elevation change, and all of that great data from my wrist. At the end of the day, I wanted to view my data on my phone. Only here was a little problem. Cell phone coverage was limited to the main roads, and even then, it was quite slow 3G. Again, this was 2015, and it was too slow to upload all of my data from my smartwatch to Fitbit servers. While the upload made steady, incremental progress, Fitbit servers would cut off the connection after 2 minutes. I tried and tried, but just kept failing after 2 minutes. Now, I was working as a software engineer on Fitbit's web API at the time, and I had a hunch about the reason. Our reverse proxy server timeout was set to 120 seconds. We just hadn't anticipated the possibility of a half megabyte at most of data taking longer than 2 minutes to upload. Now keep in mind, that's slower than a 56K modem. My smartwatch and my smartphone, they were not so smart when in the wilderness. And it had some of the capabilities, like collecting the data and seeing some of the data on my watch, but I couldn't get the full experience on my phone because of intermittent internet connectivity. Now, this connectivity problem was on the client side, but problems can exist on the server side as well. And that happened to Fitbit's competitor Garmin in July 2020. A hacker gained access to Garmin's internal computer systems, and it held the company hostage for 5 days, demanding $10 million. It's unknown if Garmin paid the ransom, but for 2 days it went completely offline. So most Garmin smartwatches, they just didn't sync for 2 days. But server outages are not caused exclusively by hackers. If you've ever used Amazon Web Services in the US East 1 region, you know this. AWS is the most popular cloud infrastructure provider in the world with around 33% market share. And the US East 1 region is its most popular data center. It's the default region for many of AWS's services, and it's typically the first region to get new features. That means a significant portion of what you do online every day touches AWS's data centers. So, what happens when it goes down? Well, we don't have to imagine because we get a reminder every few years of what happens. In December 2021, AWS US East 1 region went down 3 separate times, and the worst incident was for around 7 hours. Popular websites like IMDb, Riot Games, apps like Slack and Asana, they were just down. But websites and apps that depend on the web going down is kind of expected in such an outage. More interesting to me, however, is that floors went unvacuumed during this time because robotic vacuum cleaners, they stopped working. And doors went unanswered because Amazon Ring doorbell stopped working. And people were left in the dark because some smart light brands couldn't turn on and off. But at least they eventually started working again. Now, I've mentioned hackers taking servers offline and cloud providers accidentally taking themselves offline. But another way that servers go offline is when you stop paying for them because your company goes out of business. In 2022, smart home company Insteon abruptly ceased business operations one weekend. Its customers' home automations for lights, appliances, door locks, and such, they stopped working without warning. Emails to customer support went unanswered, the CEO scrubbed his LinkedIn profile, the company just vanished, and millions of dollars in smart home electronics became e-waste. Thankfully, some of its customers connected with each other on Reddit, and they started reverse engineering protocols, building open source software, and eventually got together to purchase the dead company's assets. It was a triumph of the human spirit, or at least some rich techies with some free time. But the point of my story is that so many of the physical devices we now own require not just electricity, but a constant internet connection. They're right beside you physically, and yet a world apart because they can't connect to a server on another continent. Okay, final set of stories. There's this internet meme. There is no cloud, it's just someone else's computer. The point of this meme is not to disparage the genuine innovation of seemingly boundless computational capacity available instantly with just an API request and a credit card. The point of this meme is to remind people that when you put your data into the cloud, you are entrusting other people to take care of it. And unfortunately, the companies and the people who work at those companies do not always do the best job of that. In 2021, security camera company Verkada had thousands of customers. Big corporations like Tesla, hospitals in 3 US states, several US airports, and even Sandy Hook Elementary School. Its products not only provided video surveillance, but also facial recognition of individuals in the video. This data was extremely sensitive. And one day, Verkada's customers got an email informing them that hackers had gotten access to a so-called super admin employee account. This account allowed hackers to see all of the live video feeds and archived video of all Verkada's customers. This was a huge breach. The most interesting admission by Verkada was not that a security breach had occurred, but that there was an employee account with this level of access to its customers' data in the first place that could be hacked. Just a year earlier, a whistleblower at the company went public with accusations that Verkada employees were abusing the level of access that they had to customer data. They alleged that some employees were taking screenshots of women in the security feeds and sharing them internally. The company, of course, denied this, but hackers confirmed that this capability still very much existed a year later. Just 2 months ago, Tesla went from being a victim of Verkada to being accused of doing the exact same thing. Tesla cars are equipped with a bunch of cameras for its autonomous driving and safety features. 9 former employees now claim that for years, Tesla employees would share images and videos from customers' cars in internal chat groups for amusement. One employee said, "We could see them doing laundry and really intimate things. We could see their kids. We could see inside of people's garages and their private properties," said another. But Amazon Ring, however, it truly wins the prize. It not only has extensive allegations of broad employee abuse of customer data and being hacked multiple times, it also has admitted to giving police customer data without user consent, and sometimes even without a warrant. In one case, Ring not only provided the data requested, but additional video inside a customer's home that was completely unrelated to the investigation. People just wanted a way to easily unlock their door, and they accidentally helped create a police surveillance state. This goes beyond invading the privacy of individuals to potentially harming all of society. So this is the present state of things. I've shared stories about internet-connected products not working well when the internet connection is bad, not working at all when the servers are down, and actively working against us, against their users, when that trust is misplaced. The central theme to these stories is the cloud architecture. So does it have to be like this? Are we stuck with the internet of shit? Well, let's look at the smartwatch example and try to figure out how we could achieve the same user experience in a way that works offline, doesn't rely on trusting someone else to protect your data, and doesn't become e-waste if the servers go away. So the typical present-day architecture, it looks something like this. The watch communicates with an app on the phone via Bluetooth to relay data from the watch to the server because the watch itself, it doesn't have a constant connection to the internet. Wi-Fi is just not always present, and cell radios require paying for data, and they consume a lot of power from a tiny battery. The server then does the processing of the watch data. It sends it back to the phone, which loads the state back onto the watch. And then when you use the app makes a bunch of API requests to the server to retrieve the watch data, but reformat it in a way that's easier to use as an app developer. So for example, the number of steps that you take, that can be represented as a daily summary, a minute-level time series, and as progress against a daily step goal from a specific workout. Another example is processing raw GPS data. If you've ever looked at raw GPS data, it kind of looks like a scatter plot of points with varying levels of calculated accuracy. And it's often unusable without some smoothing. which then requires recalculating distances to more closely match reality. So, how could we make this work offline? Could we just get rid of the server? And what would it take to do that? Well, it would mean moving the logic that exists on the server into the smartphone app. And in this case, that seems like quite a reasonable thing to do. Many people's smartphones are now more powerful than the laptop computers they use, often with more RAM and storage space. And there's no significant performance benefit of using a powerful server to do these types of computations. So, getting rid of the server not only shifts the computation expense to the phone, but it also eliminates the data storage cost and responsibility of the provider. It saves businesses money and is more secure for the customer. It's a double win. The data stays on the phone, and then people can use the encrypted backup features on their phone to keep their data safe. So this proposal is not unrealistic. This is, in fact, exactly the architecture that Apple chose when it introduced its own smartwatch, the Apple Watch. The Apple Watch's cloudless architecture is inherently more secure because your data stays on devices within your control. It's more resilient because it doesn't depend on network connectivity to function. And it's more ecological because if Apple stops making the watch tomorrow, it will keep on ticking. The problem is that other smartwatch makers have not chosen to imitate this cloudless architecture of the Apple Watch. And this problem is not limited to smartwatches. Many smart e-bikes and most smart home products, they work exactly like Fitbit's cloud architecture. Companies and developers, they seem fixated on cloud services. And why is that? Well, the cloud web service architecture is pretty much the default choice today. It's established and it's easy to get consensus to build. There's a ton of tooling to support building products this way. It's great for business because companies can justify a subscription from a recognizable ongoing operation cost and then get recurring revenue. And marketers love it because they can mine customer data stored in their cloud for insights without asking for permission. So, to change this, I think we need to name the alternative to the cloud architecture and describe the characteristics that help people understand the trade offs. We need to describe it by what it is, not just by what it is not. So, today, I'm excited to share with you the Leaf computing architecture. The Leaf architecture defines software that is locally executed, which means the business logic happens on a device within the user's control, and the user's data is stored without having to trust another party. Leaf software is autonomous, which means as little reliance as is possible and practical on external sources for capabilities. And Leaf software is federated, which means it prioritizes interoperability of capabilities and data portability across multiple providers. Now let's go deeper into each one of those aspects, starting with local execution. So local execution is about two things. Where does the code run and where does the data get stored? And this might sound similar to another idea called offline first. Alex Fayerke wrote about apps being offline first in 2013, and he advocated for moving logic to the client side to work offline, and then using client databases that were sync friendly so that they could share and receive an updated state with a server when that connectivity was restored. So this reduces a server to only doing things that the server is necessary to do, such as mirroring the data for a backup or for facilitating multi-user or real-time collaboration. So in the case of client apps, local execution has much to be inspired from offline first techniques. But local execution is more about who controls the device, where the logic and data storage happen. It's also possible to think about local execution happening on a server that is intended to be always online and is under control of the user. So before software as a service became the norm, software companies, they used to release software that IT departments installed on their own local servers, often in the office buildings where people worked. Today, the best-in-class software, it just isn't made available in this way. And even if it were, there is not an easy and reliable way for organizations to administer their own servers. We have some self-hostable open source alternatives to Slack, Jira, Confluence, and so on, but many of them just aren't as capable or as user-friendly yet. And they also require people who are Kubernetes and Linux admins to keep them running. But why can't we have an office server with apps that are as easy to install and update as they are on our smartphones? Well, I predict that someone eventually will make the server equivalent of an iPhone in an app store. And when that happens, local execution will be possible for both offline first and online always apps. By the way, Nextcloud is one company trying to realize this dream. It still has a really long way to go, but I'm cheering them on. So next up, Leaf software is autonomous. Now, local execution and being autonomous go together quite closely. Software is autonomous when dependencies on external servers are reduced to as much as is necessary. Now, this does not mean complete isolation. I like to think of it as cloud assisted software. The power of the web is in part our ability to build and share unique capabilities over a network. And we don't want to lose that. It's just that autonomous software is further empowered by those external dependencies, not powerless when those dependencies are unavailable. Lastly, Leaf computing utilizes federation. Now, federation is just a fancy word for playing nicely with each other. It's a spirit of cooperation between products. And in software, it means sharing data formats and protocols. So when available, we opt to store data in commonly used data formats. And if no format is available, then we document and invite collaboration on the data format. We don't want to hold user data hostage by proprietary storage format. Many products can interoperate simply by reading and writing data in an agreed upon format. But other times, we do need to define protocols or APIs so that products know how to communicate with each other because maybe it's not data, but a capability that's being shared. So to recap, Leaf computing describes software with an architecture that is locally executed, autonomous, and federated. It's appropriate for products where the user is authoritative, and it's not appropriate for products where the user must ask for permission to do things. So, for example, the Leaf architecture, it's not appropriate for an online store where the store must manage inventory and confirm payment. Now, let's try to apply this by redesigning a smart home air purifier from Miele. Now, this product actually exists today, but it uses a common cloud architecture. And I want to redesign it to get rid of the cloud and use the Leaf architecture. So this smart home air purifier, it automatically senses when the indoor air quality is bad, and it adjusts its speed accordingly. And it also has some nice features like the ability to set a white noise generator when you're sleeping from its mobile app. It's super smart, so I excitedly buy it. I take it out of its box and I plug it in. And to connect it to my home network, I push the Wi-Fi protected setup or WPS button on my router, and it just magically joins my network. WPS eliminates the complicated pairing process or remembering your Wi-Fi password. And a smart air purifier, it's basically just a dumb air purifier, but with a web server serving a progressive web app and APIs on board. Now this one, it uses zero configuration networking, also known as zero conf or Apple Bonjour, to make itself easily discoverable on the home network. And the screen on the air filter, it tells me to go to airfilter.local on my phone's browser. And when I do that, I see a little web app that shows me the history of the air quality. It also has that setting for scheduling the white noise mode for when I'm sleeping. That's neat. And this configuration data and the historical air quality data, it's all stored on the air purifier itself. Now, what if I want to be able to control it when I'm not on my local network? So let's say I go on vacation and I forgot to turn it off, and I don't want it to use electricity because electricity prices are expensive right now. Well, the challenge is that I can't connect to a device inside of my home from the outside easily because of network address translation and opening ports on my router is complicated. So the typical way that smart home device manufacturers deal with this is to move all of that control logic and configuration data back into the cloud. But we want to keep this air purifier as autonomous as possible. So fortunately, we have another standard called WebRTC that allows for peer-to-peer data connections. It's what's used in many video chat apps today. I'm not going to go into the details of how the sequence diagrams for how it works, but the important detail is that it allows for two parties on separate private networks to establish a peer-to-peer connection with only a cloud assist to get it started. So the air purifier company, it hosts a website for this cloud assist. My smart air purifier, it connects to this website, and then it shows me another link on its screen that I can go to on my phone. And I bookmark it or save it to my home screen. And now when I go to this website on my phone, the website facilitates a peer-to-peer connection to my smart home air purifier using WebRTC. The air purifier then serves its progressive web app and the data to my phone just like it would as if it were on my home local network. The cloud server does nothing else. The app in my phone and the air purifier are talking directly to each other once initially connected. Okay, but now what if I want to get a notification for when the air filter needs changing? Okay, great, no problem. The smart air purifier is serving a progressive web app, which means that it can use the web push API to send notifications, just like a cloud hosted or native mobile app would. All right. But now, what if I wanted the smart air purifier company to we wanted to use machine learning to detect when mold is more likely to grow in high humidity and then preemptively filter the air more before the mold can start to grow and become a problem? Well, the company could use something like TensorFlow.js to run machine learning models directly on the smart air purifier itself, maybe even in a WebAssembly container. And again, we'll use a cloud assist to get the current weather forecast data from some API provider, and then match it up with the air purifier's own sensors and run that machine learning model to predict and protect. The Superface, it's a neat product that allows you to do a single API integration and then flip between providers as desired. And this enables federation even when the providers refuse to agree on a common protocol. Okay, but now the air purifier marketing folks, they want to know more about how customers actually use the smart air purifier out in the real world. Is there any way to get telemetry data without invading people's privacy? Well, yes, there is. Some smart researchers at Stanford University came up with PRIO, a privacy preserving system for the collection of aggregated statistics. Mozilla has actually been using this in Firefox since 2018, and it enables learning about how users use the product without being to identify individual users, so their privacy is protected. Of course, the air purifier does ask for permission to participate in aggregated statistic collection first, but I agree as a customer because I know that products get better with data informed decisions. So sweet. We've now re-architected the smart home air purifier so that it uses locally executed software to serve a progressive web app, store configuration data, and run local machine learning models. The smart air purifier is autonomous, operating without the cloud when on a private home network, minimally without a cloud on the public internet, and only using weather APIs for real-time data that it otherwise couldn't have itself. And the smart air purifier benefits from federation because it can choose amongst a variety of weather data API providers for that advanced functionality. It's not locked into a single vendor. Now, I know that this is a simplified example. A real world use case would need to account for the device being put on the public internet for some reason, use on routers without the Wi Fi protected setup, multiple smart air purifiers on the same network, and defensively securing the device. But my hope is that you got an idea of how to start applying the Leaf computing architecture. By creating software that is locally executed, autonomous, and federated, we get products that are more secure, more resilient, and not at risk of becoming e-waste prematurely. The Leaf computing architecture benefits the user while reducing the security risk liability and the operational costs for the manufacturer. And what's great for the environment is also great for the wallet because you aren't paying for as many server resources. So I'm going to be posting more information about this to leafcomputing.net, but I hope that you join me in creating technology products with these ideas. The future will be bright and sunny when it's a lot less cloudy. Thank you so much.